Howdy folks, welcome back to CS 128 Honors, and Happy Chinese New Year to those of you that celebrate it. These are our goals for today, and let me move my camera. Okay, these are our goals for today, and without further ado, we'll go ahead and get started. So, some quick course announcements. Homework 1 releases tonight. We will review it together at the end of today's lecture. MP0 will release on Thursday, and you'll review that together at the end of Thursday's lecture. Other small things, I've made some updates to my setup. So we now have a pen, and I can do fun scene transitions, like moving my camera into the correct location, and even more fun scene locations, like taking a look at what's happening on the quad right now. It's raining. Okay, back to the lecture. So, quick course reminders. Are you in the Discord, and are you in the Prairie Learn? The Discord is the major way that we're going to be communicating with you all, so please make sure you're in there. Office hours, which we should be releasing tonight, are also going to be held in the Discord. If, for some chance, you cannot join the Discord, I'm happy to accommodate. Reach out to Neil or myself or both, and we'll help figure it out. Either get you in the Discord or make it so that you won't need to use the Discord. Keep you up to date in another way. So, some quick comments on homeworks and MPs. From this point on, they're going to be a regular release schedule. So, every lecture is going to have an accompanying homework. The homeworks are approximately 30 minutes each, 20-30 minutes. Something like that, just for y'all to get some practice. If one of them's a little bit longer, we'll make the other one a little bit shorter, just to account for that. MPs, and these are due 1 week after they're released. So the homework that we're releasing tonight is due next Tuesday at 11:59 p.m. CST. MPs are released after lecture, so Tuesdays, Thursdays, and they're due a little bit more than 1 week after lecture. There's 4 MPs. The first one is due, I think, 8 days after it's released, so this Thursday, and it's due next Friday. The other ones are, I think, 11 days, and 15 days, I want to say. But we'll talk about these as they approach in the future. We're happy to grant extensions if you need one. The requirement that we make, if you don't have sort of some valid excuse that would work for some normal homework or tests or things, is that you've made some progress on it. So the homework's okay. The homeworks generally take like 20-30 minutes, and so I don't foresee a lot of you needing many extensions for those. Additionally, I think your lowest 3 homeworks are dropped, if that's what the syllabus says. I can't remember if it was 2 or 3. It's whichever one the syllabus says. So your lowest couple are dropped, and I think there's only 12 of them total, and so a good percentage of them. If you miss, it has no effect on your grade. And then for MPs, this one's a little bit more likely if you do need an extension. The number one thing that we're going to look at is if you have started it already. Are you passing some of the test cases? Have you written some code? Have you made some significant progress? If you haven't, if you opened it 10 minutes ago and then you messaged me and it's 5 minutes before the deadline and you're like, can I please get an extension? I'm going to unfortunately say no. There's plenty of time to start these ahead of time. We're not expecting you to always 100% of the time never need an extension. But we do expect y'all to get started on these more than sort of the day before, right? Or the night before, I should say. Okay, and at the same time, it is a little bit tedious for us to grant extensions. Not difficult by any means, but, also if you ask for an extension on like every single MP, I might be a little bit sad. Okay, and then homeworks are going to have this feedback survey at the end. This is just an opportunity for you to put questions, comments, concerns, funny jokes, puns, cool resources, whatever you want. Talk to us, talk to staff, talk to your fellow classmates, and we'll put fun messages on lecture slides, things like that. It's really just a space for you to interact with lecture in some meaningful way. So we'll keep an eye out on those. Yeah. So without further ado, let's start to review some material. So you learned about variables and mutability. We have some integer x assigned to the value 128. We attempt to reassign it to the value 199.128. And of course, this will not work. What we need to do is make sure that x is mutable. But the keen of you might realize that this is, we'll just say some u size, and this is like some f32. Can we reassign x if these are different types? Does mutability save us here? Or do we need some other technique? And of course the answer is we do need some other technique, and shadowing is the answer in this case. So just redefine x, have it be used for something else. So just some really kind of core tools there. Keeping track of mutability of your things is very important so that you don't have to recompile your code 10 trillion times. Data types you learned about: ints, floats, chars, strings, string references, things like that. We'll discuss compound data types today, tuples and arrays, in just a bit, actually. And you learned about control flow, if statements, else if ladders. Hopefully y'all are familiar with this. If not, more than happy to cover it more. Just mention so in the feedback points on the homework. And then also we'll briefly mention some more powerful control flow: loops, returning from loops, while loops, for loops. So loops, yeah, this was sort of in the to-do. It was just sort of very small. So no saying this wasn't in the things to cover for today. And we'll only cover this very briefly because it's relatively simple. So loops do exactly what the name suggests. It executes this line and then loops back to the top and goes again. So in this case, this code would print 0, 1, 2, 3, 4, ... until you kill the program. This will run forever. You can return from loops. So we can use this break keyword and then return some value from this loop. And as long as you have a semicolon here, and as long as like val is mutable, we can put this val u into val. We can return from the loop and reassign the value into val. And so what this code will print is 0, 1, 2, ... and then 128 times 128, which, okay, this is like my third time trying to remember what this number is. I think it's like 16,386 or something. It's some power of 2. If I got that right, good on me. This might be a 5. We'll see. Okay. I don't know. Someone pull out a calculator and do it and let me know in Discord, I guess. Okay. And so, yeah, you can return from loops, which is pretty powerful. And in fact, this pattern of sort of returning from things you might not expect to be able to return from is a common and extremely powerful thing that we can do in Rust. So it's not only loops, very notably it's match statements as well, which we'll learn about later. While loops also exist, of course, just like any other language, we can do while loops. This is the syntax for this, just while, some condition. You can do and or in these, and however you want, same as always. You can put parentheses here. The compiler will tell you that it's not necessary unless it is, which if you have some multiple case statement, it is, or like val is not equal to this and some other case. Condition maybe is the more appropriate term. Okay, and eventually anyway we exit this while loop and we print the final statement. So that is the exact same as the previous case, just using a while loop instead. For loops also exist. So for loops, you can iterate over some iterable. This can be something like an array or a tuple, which we'll look at in a bit, or it can just be a range of numbers. And this is how you can do that in Rust. So you say let me say a ... and this will start with a, and it will end with b minus 1. So in this case below, what we will print is 0, 1, 2, 3, 4, ... 128, but not 129, because it's non-inclusive of this. If we did want to print 129, then instead of this, we can write 1 ... equals 129. And then we would include 129 here. Otherwise, we won't. Okay, for loops, while loops, these stuff, they're relatively straightforward, not too crazy, not very specific to Rust either. The syntax is maybe a little bit strange, like this weird double period. You'll get used to it really quickly, so I'm not too worried about it. And, let's talk about some of these compound data types. So you learned about some of the sort of primitive types in the previous lecture with Neil. Ints, strings, floats, things like that, chars. Now we can talk about compound data types, which is a collection of these data types. The major two ones are tuples and arrays, the two primitive compound data types. There's another type that we'll briefly discuss later called vectors, which are, to be honest, extremely useful, and you'll use a lot, but we require this idea of ownership before we get too far into vectors. Okay, and both of these are fixed length, which is maybe important because not all arrays in all languages are fixed length. For example, I think in, I don't know, Java or something, these are variable length. In Rust, they're fixed length. Think of this as, both of these types are some constant amount of memory. They are sitting in some block. You're putting the 1 here, the 2 here, the B here, and then the string here. And so, obviously this has to be fixed length. Tuples can support multiple types, an int, a float, a char, a string, right? Arrays all have to be the same type. But again, these can be any type: ints, floats, chars, other arrays, vectors, things like that. Okay, and we can look at the syntax to do this very briefly. For tuples, you just wrap everything in parentheses. They can be whatever you want. They can be even emojis. We discussed briefly that emojis count as characters, which is fun and cool. You can also type your tuples, which is important, especially if you have a tuple that is maybe a return value from a function or a parameter to a function. You do need to specify what the types of these are. And this is how you do that, just like you would an int, except we sort of have this tuple typing syntax with the parentheses. Relatively the same though, right? If we wanted to do this with some variable, we'd say let x, I32 equal 5, right? With the tuple, only difference is we have those parentheses and the types of each one. We can destructure a tuple, which is the equivalent of saying let a equal 1, let b equal 2, let c equal crab, and let d equal rust is cool. And we can then sort of use these variables however we want. So in this situation, we'll print out c, which is crab, and then d, which is rust is cool, and then c, which is crab again. So crab, rust is cool, crab. But you don't have to destructure a tuple in order to use its elements. You can directly index into it with this syntax. This is a little bit different than the square bracket syntax that you see in other languages. It's important to note this square bracket syntax is what you use with arrays, but not with tuples. So with tuples, you use the dot syntax. There's a great reason why this is. Technically, tuples are what we sort of call tuple structs in Rust, and you're accessing this element of the struct, but I won't get too far into that yet. And this does the same thing. So we access the second index, 0, 1, 2. This is 3. So this also prints crab, rust is cool, crab. Arrays. You can instantiate arrays with the square brackets. Hopefully not too surprising, sort of how you expect it to be, 199128 in this case. Arrays can be typed. So in this case, we're saying I would like to create an array of 6 unsigned 8-bit integers, and the values are going to be 199128. And in fact, you can even sort of do it in a little bit of a fancier way. So you can just say, I want an array of 6 unsigned 8-bit integers that are uninitialized. We'll look at what happens in a bit. And then you can also say, I want an array of 6 ones. And by default, usually this is usize. You can also type this one here if you want, but if you just put some number, it'll be usize, usually. Okay, and of course, we can then sort of start to change the values in the array. This will need to be mutable to edit the elements in the array, but let's actually do this sort of example. So the goal here is we start with an array of 6 ones, and we want to end with an array of 199128. And this would work if it is correct. So live demo time, I will go here. Okay, so we have some function here, and I've simplified this code a little bit. So we create some array of 6 ones. We print out the values in that array, and then we want to reassign the values to some new value. So we have some function which takes in a 0 and gives us a 1, takes in a 1 and gives us a 9, a 2, a 9, a 3, a 1, etc., etc. And then eventually we want to print it out again. And really the key here is I want to sort of outline how to create a function. The way we actually implement this function isn't important, and I'll probably do it one of the least efficient ways possible, but it's fine because, I don't know, it doesn't matter. So the key to creating some function is the syntax, which is a little bit sort of new to Rust or unfamiliar, different from other languages, but it's not complex and it is easy to learn. So say we want to create some function. This is the basic syntax. So we use the function keyword, we name it whatever we want. It takes some parameters, which we'll define in a second, and it executes some code within. Now, let's first talk about parameters. Parameters must be typed and they must be named. So first, the name of any parameter. So this is some value. And this type needs to be whatever we expect to pass into this, okay? In our case, we briefly discussed how the default for this is going to be usize, right? And so this will be a usize. Now, of course, just as easily we can add another thing, and we'll just call this like s. And this could be, you know, a string, and then we can add another one that's called some random letters, and this can be, you know, a char. You can have any number of parameters you want, as long as you're actually passing them in when you call this function. Okay, but we'll just call this one x, and it'll be usize. Now, returning from functions. You need to also type the return values. So in this case, we want to put it back into the array. And we know that this array is an array of usize. But just as easily, you know, we can return a float32, maybe not in this specific case. You could return a tuple of like float32, char, string, you know, many sort of options. It's a function. You have full flexibility. This pattern syntax that we see here, that we see here, that we see, you know, not quite here, but we've seen in the past, is always the same, right? You're just sort of matching what types you want to return. Okay, we want to return a usize. And so, you know, we can say, just as a quick example, return 5. And this will do what we expect it to do. This will always return 5, and it will overwrite all the variables in the array to 5. Okay, now, you know, we don't necessarily want it to do that. We want it to do something a little bit more fancy. And so we can write some cases. We can say, okay, if x equals 0, return 1. And, you know, we can repeat this. We know that it's only going to be these cases, so I don't have to sort of be careful with else statements. 9, 9, 1, 2, 8. And we'll run this. And what we see is we actually get an error. So what happens if none of these case statements hit, right? So this is important, which is the Rust compiler is going to check all of the sort of situations that you'll find yourself in. And if what ends up happening is this function isn't going to return, or in this case, it's going to return an empty set of parentheses, which we'll talk about in a bit, what that means. You know, this function isn't actually operating how we said it was going to. We said it was going to return a usize, but it's not. So, okay, in this specific case, I don't really care about edge cases, so I'll just return 0. We know that we're not going to get there. And we'll run it again, and we see that this is successful. Now, okay, this isn't the only way to do it. You know, we can kind of treat this as like some like graph problem, and okay, I'll just copy and paste this code for the sake of time. Okay, we can treat this as some graph problem where we have like some polynomial, and you know, we go like this, basically, or what is it? We have like 0, 1, 2, 3, 4, 5, and we want 1, 9, 9, 1, 2, 8. And so this is some formula that I found online that will give us those correct values at those points, right? And we can run this, and this will work the exact same. Only sort of case that we have to care about here is converting to and from float32s and usize for the calculations. Very important that you keep that in mind. Using the pow_i formula in order to do exponents. Okay, but nothing too crazy here. Again, the implementation of this actual function inside doesn't matter. The important thing is that this, you know, sort of the input types, the output types are remaining the same, you know, and that's really why we use functions, right? Or that layer of abstraction is one reason, I should say. Okay, let's go back to the slides. And let's continue. Okay, and there's this distinction between these two things called statements and expressions that I want to make. A statement is an instruction that is performing an action and does not return a value. And an expression will evaluate to some value and return that value. So many of the lines of code you read are statements, but most things are expressions. And what do I mean by that? Okay, when we say let x equal 5, this performs an action and returns nothing. Okay, this does not return a value. This is a statement. When we say function main parentheses colon any code, anything, and then closing, oh, that's a really bad opening and closing bracket. I can do better than that. Okay. Maybe better. Okay, this is the statement, right? And, you know, sort of a litmus test to check if something is a statement or not is to just say, can I put this here? So I can say let x equal something, semicolon. Can I put my thing here? If I can, it's an expression. If I cannot, it's a statement. You cannot put let x, or let me just write the whole thing. You cannot say let x equal let a equal 5. Even if you get rid of this semicolon, this is not valid because this let a equal 5 is a statement, not an expression. But there are many things that are expressions. And in fact, expressions are sort of very important in Rust. So for example, we'll go back to the code screen. Expressions. Any mathematical operation is an expression. Any function call is an expression. When you're calling a macro, that's an expression. When you create a new scope block, that's an expression. And in fact, we even saw an example of using these expressions a couple slides ago. As I furiously click back slides. We saw here, when we want this loop to be not a statement, but an expression and return something, we could do that. And we could add the semicolon and place it here, right? And so loops are expressions. And I'll go back. Okay, this does relate a little bit to some syntactical changes that you'll see in functions. And specifically, this is the case that you'll notice we don't have a semicolon here, and that's okay. In fact, we don't even need the word return here. The important thing here is you can end a function with an expression, and it will return that expression. Now, here's an important case. This is because I can say right now, let x equal tmp as usize, right? Could I say let x equal tmp as usize semicolon? Of course the answer is no, but is this actually backed up? And the answer is yes. And once again, we see this empty parentheses. This expected usize is a return found empty parentheses. This is what we call the unit type. It's an empty tuple. It represents the lack of a thing. There is nothing here because this expression, this statement, once we add the semicolon, doesn't return anything. This becomes a statement when you add the semicolon. So you can have just an expression at the end. You can have return, which is still just an expression at the end. But you can also have a statement, return. And this will, because we're using the return keyword, act how we expect it to. But, okay, so just don't get thrown off if you ever see something like this at the end. That just means it's returning it. And in fact, if we go back to that one fun example where we returned 5, you can just put 5. And that's a completely valid function that works. You can put 5 times x. Again, this is it's a mathematical expression. Therefore, it is an expression, right? Okay, fade back and continue. Okay, so let's talk a little bit about match statements. I'm going to go over this part pretty quickly because I think we're getting pretty close to time. I did this in 2 parts, so I'm actually not quite sure what time we're at right now. But in either case, the match statements are another very, very powerful tool that we can use in control flow called match statements. And what we do here is we compare some value to a series of patterns. And we've used this word a couple times, and it'll come up a lot in Rust. But anyway, and then we execute code based on which pattern matches. Let's look at the basic structure of these. One important note is the patterns have to be exhaustive, so they have to cover every case. And you'll see in tomorrow's or Thursday's lecture why they're used with enums a lot, because enums are very easy to cover every case with. Okay, but for example, this is sort of the syntax. We've matched some value, pattern, expression, pattern, expression, pattern, expression. Of course, we know what an expression is. Another fun fact is this entire match statement is an expression. So you can return from a match statement, which is also very powerful, as long as this expression returns, or whichever pattern you enter needs to return, and then that will get returned into X. So very powerful sort of tool there. In fact, you can have just a match statement as this is the last line of your function. And because we have no semicolon here, we're ending our function with an expression. And so we'll return whatever one of these returns, which is very powerful, extremely powerful even. So let's look at some quick examples. We can have, for example, matching on a number. We'll say let dice roll equal 9. This is an example from the Rust textbook. We can say, okay, if dice roll is equal to 3, then we call some function. If dice roll is equal to 7, then we call some function. Else, if it is some other thing. Now, this other is not a fancy keyword. This is just catching all of the other cases. It wasn't equal to 3. It wasn't equal to 7. And so it is some variable. And so we pass this variable into some function. And this is extremely powerful because, we have this way of handling these other cases, and we get to keep track of the actual value of the variable by passing it in, which is super, super powerful. And so you can even do sort of fancier match statements. So this one might be particularly useful for your homework, cough, cough. You can have some string, which we'll call Eustis, and you can match cases on the string. So we can say, okay, if it is Eustis, or it is Welby, or it is Neil, then give me this string from person, right? Or return the string from person. Else, and this is a special operator. This underscore operator effectively says match everything, okay? Of course, we can't start it with this, because the match statement will enter whatever first branch is correct. It fits whichever of the first patterns fit, it will enter, and only that one. And so for this one, it matches everything, which makes this exhaustive. And then it will just have the string, not a person. Now, one important note is that this function doesn't really do anything. If this wasn't the main function, you might be able to remove this semicolon and return directly person, not a person. Or, potentially, if it is a homework problem on homework 1, maybe you return something like person. For this case, you match some other cases and you return animal or X and Y and Z. But you also have to make sure, you're getting this exhaustive case here, right? In which case, I don't know, maybe it's an invalid something. Okay, this is maybe a little bit on the nose. It's a hint for the homework, but this is a good hint for the homework. Okay, I'll quickly move through the other ones. There's 2 enums that are of particular importance that I want to introduce, just so y'all are familiar with them, and you'll see them all over the place. These 2 enums are result and option. An enum, which we'll talk about more on Thursday a lot, is a type, or rather a tool that allows us to define a type by enumerating its variations. And we'll see what this means in a bit. For example, if we have an enum for coins, its possible options could be a penny, a nickel, a dime, a quarter. We could have an enum for the states, and it could be all of the different states. You could have an enum for a calculator, and its options could be, the addition operator, the subtraction operator, the multiplication, the modulo, the division operator. Cough, cough, MP0. So maybe another small little hint right there. And there's 2 enums that we really want to introduce early, which are result and option. The result enum represents the success or failure of some operation. There are only 2 cases. Either it is okay or it is an error. Why does this matter? Well, if we, in our code snippet here, if we want to open some file, but that file does not exist, maybe instead of terminating the program, we want to create that file. So what we do is we this file open returns f. F is the type of f is actually a result enum. F is a result. And so if f is okay, then we are ready. Our file is our file. If f is an error type, then we can, throw some error, create the file, handle it in some other way, right? This T represents a template class, which just means it's anything. It's whatever you were originally intending to return, basically. In this case, the T is whatever this file type is, right? If you're writing something that's returning a result type, this could be, you could have your function, something along the lines of function A, B, C, which has some parameters that I'm going to skip, returns, result of, in32, for example, right? So, we're just saying our result type is going to have an int32 inside, and you'll see this a lot, especially in the MP. I think we use this. So this is the first one, result and option types. You can match on them, which is very powerful. We'll talk about unwrap as well, which is a powerful tool. The second one is the option enum type, which just represents whether or not a value exists. So say you're expecting some user input and they don't input anything, or you're searching an array for some element, but that element isn't in the array. Okay, so just a quick little code snippet here. If we have some function find item in array, and this returns some option of, I32 representing the index of that element in the array. Of course, 128 is not in this array. And so we can match. If it is some, if we have some value, then we just want the value. If it is none, then we maybe need to throw some error, right? Okay, you'll see a lot more of this, so if you're a little bit confused, don't worry about it. We'll cover it a lot and a ton of examples. It is still valuable to introduce you to these concepts early on rather than later. Okay, final thing, vectors exist. They are variable length. They generally require the same type, though there's some interesting workarounds for that. But yeah, they're variable length arrays. They're very, very useful, and you'll use them a lot in the future. We won't cover them yet. We'll need to cover ownership before we cover them too much. Okay, and then let's also look at the homework together. I'm going to go not too fast, but like relatively fast because I know we're low on time. Okay, so this is your homework. This is maybe the staff perspective, but it doesn't really matter. This part's the same, which is important. So you have 4 major tasks here. The first one is some function that checks if the integer is beginning with a 1, 2, 3, 4 or 5 and returns 100 level, 200 level, 300 level, 400 level, or grad course. If the number is specifically 128, of course you have to return the best class. This one's relatively straightforward. I recommend approaching this in an if statement way if you want. If you want to get fancy, match statements can make this a much quicker process. If it does not fit this pattern, though, you do have to remember you have to return invalid course number. Of course, if you want to check if it starts with a 1, 2, 3, 4, whatever, you can just modulo on this and make sure it's equal to, divide by it, integer divide, and make sure it's equal to that thing. Okay, this next function is relatively straightforward. Return the value 3.5 with double precision. So not float 32, but float 64. The next one, you return the rust crab emoji as a char. We've gone over how to return things from functions. If you remember, we created some function. I'll just call it 5. Takes no parameters. Returns some int32 or some usize, and we can just have the number 5 here. Similarly, this can be adjusted for the rust emoji. Change this, change this, change the name of the function since it's supposed to be called return rustation. Okay, and then the last function is a little bit differently. This is very important that you get the function parameter and name correct. This one you will have to write yourself. So the name of the function is match item. It takes a single parameter called item, and that type of item is a string reference. That's what we call this, @string. And it returns a capital S string. Okay, so you all know how to type a parameter and type a return value. One useful function that is good here is this string from Eustis, for example. So this, if you have, so if I say, for example, let x equal Eustis, then x is a string reference. But if I need a capital S string, then I can say let y equals string from Eustis, then y is a string. So very useful to convert these two things back and forth. And specifically in one of the previous slides, we did look at an example of using a match statement with a string reference. So I encourage you to go back and use that as a reference for these cases. Additionally, the last thing that I'll mention is that there are a large number of tests that we have written for you within this zip file, as well as instructions on how to write your own, as well as how to run the tests. So you should have, for this first homework, more than enough exhaustive tests that we've provided you that can A, act as a reference for future homeworks and MPs, and B, to make sure that you have this running locally and efficiently. Basically, the grader online is sometimes slow, and even if it isn't slow, sometimes it's just better to work locally. So we do recommend that you download this zip and you do local development, cargo build, cargo run, cargo test, to make sure that these things are working. We especially encourage this during the MPs, and of course during final projects you're going to have to work locally. There's no pre-learn for that. So download the zip, get it running locally. All should be good to go. Thank you all so much. Sorry that this video was a little bit longer. We covered a lot of topics. I hope that it was still helpful. See you around. Bye-bye.